Hello, hello, hello. Welcome. How's everyone's weekend? Doing good, I hope? So, as I posted today, we're just switching the times of the lectures to be a little bit later in the evening. I unfortunately had some scheduling problems with some stuff, and doing them in the mornings for the next 2 weeks is going to be a little difficult. So rather than release a severely inferior product, let's just do them at 8 p.m. So just 1 second. All right. So today is really exciting because we actually get to start talking about reinforcement learning. And reinforcement learning is going to be for like 4 to 6 lectures. And it's a really cool topic, and I hope people have as much fun with it as I've had with it over the years. Also, the next lecture, at the end of the lecture, I'm going to be running the tournament for the in-class tournament for the Connect 4 assignments that you submitted. So we're going to take all of the completely functional Connect 4 alpha beta algorithms that you all wrote, and we're going to have a nice little tournament, and so that will be recorded for all time to see who wins in that. So let's just get started with the reinforcement learning section of the course. Let me get the PowerPoint view up here. Here we go. Okay, so as I said, this is lecture 13. And we're going to be talking about an introduction to reinforcement learning. First, before I get into the topic, I want to say that the suggested textbook for this course, it's called Reinforcement Learning, an Introduction. It's now in the 2nd edition. It's by Sutton and Bartow, Richard Sutton and Andrew Bartow. It is the best textbook I have ever read in my entire life. I cannot recommend this textbook enough. It's extremely understandable. It has intuitive explanations of everything, lots of English. It has enough math that if you want to learn the math, you can, but you can also just read it and understand the concepts. I highly recommend reading that book as we go, especially for the final exam, because as you saw from the midterm, I'm not just asking definitions, I'm going to be testing your understanding of the concepts. So try and understand the concepts behind the reinforcement learning. The book is available for free at this URL here. I'm sure you could also grab it from a library, or you can order it online. I know it's available on Amazon, but if you don't want to spend the money, you can go to Richard Sutton's website, and it is available for free as a PDF on the website. Okay, so please, I highly recommend picking up that book. It'll change your life. It changed my life and way of thinking about things. So, what is reinforcement learning? What is the big, the big excitement about reinforcement learning in the last decade or so? So, reinforcement learning is a sub-area of machine learning, okay? It's really inspired by natural systems and psychology. And what reinforcement learning does is it's going to learn via interaction with the environment. And we'll talk about we'll compare and contrast that with other forms of machine learning as we go in this lecture. As the agent in the environment is interacting with it, the agent is going to receive rewards. So the rewards come from the environment, and if you do a good action, you're going to get a positive reward. And if you do a bad action, you're going to get a negative reward. And so the entire goal of a reinforcement learning agent is to maximize this reward. So for example, if you were a little kid and you touched something hot like a stove or fire or a cup of tea that was really hot, your your internal sense of touch triggered some sort of pain response because it was too hot. And so that was a bad action. You got a negative reward from that. And what your brain then did was associated that negative reward with, maybe I shouldn't do that again. Versus if you ate some sugar or something sweet and you really liked it, your brain would think that was a good action, then you would be positively reinforced. So all of reinforcement learning is about the agent interacting with the environment in combination with the agent getting a reward signal, and then the goal of the reinforcement learning agent is to maximize the reward. So let's first talk about machine learning in general. So there's three main forms of overall types of machine learning. There's, well, reinforcement learning, in which we're going to talk about in this lecture. And there's also supervised learning and unsupervised learning. And I'll give some examples of those so that we can see what the difference is between supervised learning, unsupervised learning, and reinforcement learning, because they are quite different. So supervised learning, what you're doing is you're learning from training data. So you're given some inputs and some outputs, and you're learning to predict the outputs for newly unseen input samples. And I'll give an example of that in a bit. In unsupervised learning, you're letting the computer or the algorithm learn from data without labeled outputs. And some examples of that can be clustering, for example. And I do have some examples of that as well. So here's kind of a really nice, this just says ML up here if my webcam is blocking it. This is a nice image I got from this little explanation article down here. And this is sort of the process of supervised learning. So let's say we've got some input raw data. Let's say that that's images of different types of fruits and vegetables, for example. I think these are all fruits, yeah. So we've got images of different types of fruits. With supervised learning, the reason it's called supervised learning is because it has to have some sort of supervisor, right? So for example, the supervisor in this case would look at, maybe it was a human, for example, it would look at all the images and assign them maybe a label. For example, this is tomato, this is an apple, this is an orange, this is a banana. So it would take all the different input images, and the supervisor would look at the training set data, and it would assign a desired output to each of the inputs, right? So again, the supervisor would see this and say, okay, that's a tomato. I eventually want my machine learning algorithm to identify that as a tomato. This is a pear. I would like it to identify that as a pear. So then the input training set, along with the desired outputs, are fed through some algorithm. There are lots of different supervised learning algorithms. We'll talk about neural networks a little bit later in the course. And then through whatever processing happens within that algorithm, this is called the training phase, okay? So as it sees, ideally, more and more images of tomatoes with the correctly labeled outputs, it's going to be more and more confident that an image of a tomato actually contains a tomato. After this has been processed, you have what's called a model, okay? So your model is essentially your prediction function. And what the model is going to do is when you give it a new input image or a new input data that's not in the training set, it could be in the training set, but it could also not be in the training set, your model is then going to predict the output of that training set. So for example here, if we gave it another image of a tomato that wasn't in the training set, the output hopefully should have learned sort of the qualities of the image that make this image an image of a tomato, and your machine learning algorithm would say, okay, this is a tomato. So this is a type of problem called classification. So in classification, what you have is a number of different sets of data. So for example, up here, you have a bunch of different inputs, and each of them has been assigned to a class. You're trying to classify the fruit. So the number of different classes we would have here are the number of different fruits that we want to have images of. So let's say we have 10 different fruits and we have 1 million different images, then your input training set would be of size 1 million, and you're trying to map those inputs or predict the output, which is one of 10 different types of fruit, okay? So that's classification. And here we see another example of classification where we have some points on an XY plane. The points down here are all circles, so that's some property based on the point. And the points up here are all pluses, and that's some other property. Let's say, for example, we talked about this a little bit in another lecture, where based on certain inputs, maybe these people qualify to get a mortgage or a loan, and these people don't qualify to get a mortgage or a loan. And so what happens here is that your algorithm, through whatever method, if you passed in another point, for example, a point right here, it would say that's probably a circle. Or if you passed in another point up here, it would say that's probably a plus. There's another type of supervised learning called regression. And regression, you can think of it as sort of a line of best fit. So rather than just try and have like an integer classifier, so it's a part of this class or a part of another class, what regression does is it tries to predict the outcome of an arbitrary function. So for example, here we see a linear regression where you're trying to fit a line to a set of points. But here we have another type of regression which is a lot more powerful in that it over time tries to learn a function with a more complex structure. Okay, so what you see here is over time, you have the training set data in light green and the test data in dark green. And what it's trying to do is it's trying to, over time, based on the inputs and correctly labeled outputs, learn the shape of this function. And then up here on the top, you see the mean squared error. And over time, as we learn, this error is going down and down and down. Okay, so those are the two main forms of classical supervised learning. We have classification and regression. Next, we have unsupervised learning. And what unsupervised learning does is you're going to give a bunch of data to your machine learning algorithm, your unsupervised learning algorithm, and it's going to try and find patterns in that data somehow. So for example, one of the classic examples of unsupervised learning is the k-means algorithm, or it's a clustering algorithm. And what it does is you've passed in a bunch of different data. For example, this is a little bit hard to see here, but the next image will show that it's a little bit, the next image is a little bit larger. Here we've passed in a bunch of image features, and those images are like handwritten characters, okay? So those handwritten characters have things like features such as how many pixels are black versus how many pixels are white. What is the structure of the image? How large is the image? Stuff like this. So what we can get over time is you take all the dimensions of those features, and then a clustering algorithm would try and group these features based on similarity. So for example here, if we took a data set of a bunch of different handwritten digits, so single digits, from 0 to 9, and then we said, hey, Mr. Clustering Algorithm, please give me, or separate this data into 10 different clusters. And what we might get out, like in this one, I apologize, I don't know the exact algorithm that was run here, is you can kind of see that all the zeros are together, all the 9s are together, we have the 5s together, the 6s, and so it's done a decent job of clustering the properties of this algorithm in whatever space this is representing. And we can see sort of an example of what clustering does. So that's called unsupervised learning. And really what you're trying to do with unsupervised learning is typically researchers will use it when they're not sure what sort of relationships exist in the data. And so they'll say, okay, try clustering it, and then at the other end, when we're done clustering, we can look at the data and see if there's any sort of patterns, etc. And now we get to reinforcement learning. So what is reinforcement learning? Reinforcement learning, despite popular belief, is not an algorithm per se, okay? It's not an algorithm. Reinforcement learning is more of a problem specification. So we have this idea of the reinforcement learning framework, and we'll see what that is, okay? But essentially, if you can frame your problem within the reinforcement learning framework, then you can use a reinforcement learning method or algorithm to solve it. And so there are many different techniques and many different algorithms that can be used to solve reinforcement learning problems. And if you've heard someone talk about an RL method or a reinforcement learning method, that is the technique or the method or the algorithm that solves a problem that fits the reinforcement learning framework, okay? So reinforcement learning is more about how you phrase the problem in terms of agents, environments, rewards, etc. And then you can apply one of many, many different techniques that can solve these reinforcement learning problems. So that's a really important point. It's not a specific algorithm. It's a class of problem. Okay, so let's deep dive a bit, or break the surface, if you will, of reinforcement learning. So reinforcement learning at its core is learning via interaction with the environment. There's no explicit teacher for the learning. So unlike supervised learning, we don't have someone telling you exactly what you should do, okay? But what's going to happen is that the agent is going to take some actions, and it's going to receive a reward signal from the environment. And I'll talk about that in a bit. The learning via interaction teaches us about cause and effect, consequences of actions, and what to do to achieve goals, okay? So what you're going to have to do, and we'll see some examples of this, is frame your problem as a reinforcement learning problem. In order to do that, you have to give it a reward signal. So for example, doing this sort of thing is good, and doing this sort of thing is bad. And then through interacting with the environment, the agent will learn what to do that's good and what not to do, which is bad. So what we're going to see happening is something like this. So we have an environment, right? So of course we know that there are states of an environment, and again, states are particular configurations of the environment. The environment and the agent will define what actions are legal within a given state of the environment. And then the environment is also going to have a reward function. So what's going to happen is that we're going to see the following loop. The agent is going to do an action, the environment is going to change its state, and it's also going to send a reward back to the agent. So the agent does an action, the environment transitions to a new state, and it sends a reward signal back to the agent. And then the agent is going to think about that reward signal, and it's going to update what it thinks it needs to do in the future in order to maximize that reward signal over time, okay? So this animation can sort of boil down to this particular loop. So we have an agent, and that agent is living in an environment. And we're going to be operating at discrete time steps. So even though, yes, the universe may be operating at a continuous time, in order to, do this in a computer, we have to have discrete time steps. So whenever we see the subscript t, like over here, that means it's a particular variable at time step t. And if we see t plus 1, then that is a particular variable at time step t plus 1, which is the next time step. Okay, so there's an agent, it lives within an environment. As an input to the agent, you have a particular state of the environment. So the agent is at a particular state, right? That state gets fed into the agent. That agent is going to look at the state, and it's going to, through whatever algorithm it uses, whatever policy method, it's going to take an action within that environment. That action is then going to affect the environment and change it somehow, right? So for example, if I picked up a glass of water and moved it, that's an action that is changing the environment. Or if I'm placing a piece in a Connect 4 board, that's an action which changes the environment. So out of the environment then, what you get is you get a new state. So you get the state at time step t plus 1, and you get a reward signal, and that's the reward signal at time step t plus 1. And based on those two, the new state and the reward, the agent is going to update its belief of what is good and what is bad, and then the next action will be reflected, those belief changes will be reflected in the actions in the next time step. So like I said before, if the agent took the action of touching a hot stove, then the environment would tell it this is pretty bad. And so the agent's belief in when I see this situation the next time, I probably shouldn't touch the hot stove. Okay, so that's kind of how it's going to work. So let's break that down a little bit more in sort of one slide. So the agent and environment interact in discrete time steps. When you're Agent starts, that's time step 0, and it's going to go up to some time step n whenever we stop. So the agent observes a state at time step t. So that is S sub t, which exists in the set of all states, okay? So this is the terminology, or sorry, the syntax that we're going to be using. The state at time step t is S sub t, and that exists within the set of all states, capital S. The agent is going to produce an action at step t. That action is lowercase a sub t. So that's the action at step t. And that's going to exist in the set of all legal actions at state S sub t. See how this works? So it's now at S sub t, and it's going to produce an action from the set of all legal actions of the agent at that state. So lowercase is sort of the current thing. So it's the current state, it's the current action. And the uppercase is the set of all possible things. So uppercase S is the set of all states. Uppercase A is a function which produces the set of all legal actions at S sub t. Because remember, when we were doing pathfinding, for example, if you're at one state, maybe you can move up, down, left, and right, but another state, like close to the wall, maybe you can only move in one direction. So the legal actions will change at each state. And the environment is going to give us a resulting reward from performing action A sub t at state S sub t, okay? And this is going to exist within R, which is the real numbers, okay? So any real valued number can be a reward that you get from performing an action. And then you're going to transition to the next state. And so the environment is going to transition to S t plus 1, which is the state at time t plus 1. And of course, that also exists within the set of all states. So if we want to take this loop and we're going to flatten it out into a single timeline, what we get is something like this. So we are currently at, down here, this goes from left to right, and it's sort of this continuing timeline. So let's say we're at S sub t, that's the current state. We're going to produce an action, and then we're going to get a reward, and then we're at a new state, and we produce a new action, we get a new reward. We're at a new state, we produce a new action, we get a new reward. And this continues until we stop the process for whatever reason. Okay? So this is straight out of the book, and this is sort of the way that the book teaches these graphs. So we have this circle, we're at a given state, then the line, the transition from one state to another, okay, from ST to ST plus 1 requires an action being performed, and from doing that action, you get a reward signal from the environment. Perfect. So let's talk about now how we might actually frame a problem in terms of this reinforcement learning framework. So this is a pretty canonical example. It's called the cart pole problem. And so what the point of this is to balance the pole on the moving base as long as possible. All right. Can I make a fool of myself by trying this somehow? Let's see if I can do this. All right. Oh, this is not the best, right? But this is not. Here we go. I can do this one. All right. So say my hand is a cart, and I'm trying to balance it, right? So it's going to lean to one side, so I have to move over to that side when it leans. If it leans to the other side, I have to do that, right? So this is what's happening. I have to move the cart back and forth, and I'm balancing it like that. But of course, that's a real valued problem, right? Sorry, it's a three-dimensional problem, but we only care about 2D problems in this course. So that's what's happening right here. So here we have this cart, and this cart is locked on this one-dimensional line. So the actions of the cart are move left and move right, essentially. On top of this cart, affixed by some like screw or something, is the pole. And so when it moves left, the pole wants to fall to the right, and so it has to move right. And you get it. You're a human. You've done stuff like this before. So the possible actions at any time step are move left and move right. And so the goal of the problem is to balance the pole as long as possible. That's the whole goal. And so the reward signal, you can think of this as while the pole is currently balanced, that's a good thing. And so you want to keep the poll balanced. So you're going to get a +1 reward for each time step that the poll hasn't fallen. And maximizing this reward maximizes the balance time. And so this is what we call an episodic task. So there's going to be a terminal state when the poll falls. Okay? Now, you may think, so the only other thing remaining is how we would actually represent the state of this environment. So the state of this environment would have several variables. So it might involve things like, so this is the x coordinate. You would have the x coordinate of the cart, right, where it is on this line. You would also have the speed. Actually, I should say velocity. The velocity of the cart. Oh, I can't draw with a mouse. I'm sorry. So the velocity in the cart in either the left or the right direction. So like how fast it's currently going. And maybe also the angle and the speed of the pole as well. Because if the pole is at over here, you want to take a different action. So it's not just the position of the cart that you want to record here. The state of the environment has many different variables. And so what you end up with is going to be what's called a policy that says if you're ever in this situation, you should move left, or if you're in this situation, you should move right. So that's how we frame a problem in the reinforcement learning framework. Here's another example. This is called the mountain car problem. And your goal is to escape the top of the mountain as fast as possible. So you start down here in this hill, and you want to move the cart all the way up to this goal right here, okay? And so your actions are accelerate left and accelerate right. And the problem is that, there's a pole up there behind my webcam. So the problem is that your engine, the physics of this environment, your engine isn't strong enough to simply just go up in one direction, right? So if you just say accelerate right, maybe your cart makes it up this far, and then it can no longer go. And so what you have to do is use gravity to sort of get yourself out, right? So you go up a bit, and then you put it in reverse, and you go accelerate downward, and you go up a bit further to the left, and then you accelerate back, and you go up further to the right, okay? So what's the reward going to be? Well, the reward is always essentially tied to the problem that we want to solve. And the problem we want to solve is to escape to the top of the mountain as fast as possible. So, in reinforcement learning, we have this little trick where if we want to do something as fast as possible, what we do is we give the agent a -1 reward for each time step until it reaches the goal. And so if you've ever seen Rick and Morty, this is kind of like the Meeseeks, right? Like existence is pain. They don't want to exist. And so if they can accomplish their task as fast as possible, that's what they want to do. So by maximizing a negative reward, you are completing this task as fast as possible. And so any sort of pathfinding or wanting to do something as fast as possible, you can simply give it a negative reward, and then by maximizing that reward, you're doing the task as fast as possible. And this, again, is an episodic task, and we'll get into the differences between episodic tasks and stuff later. But the terminal state would be when you reach the goal up here. So, what would this then look like? Well, maybe at the beginning, we have an agent which is really bad, and it just sort of takes random actions. So here we can see on episode 0 of the pole balancing problem, maybe we don't know how to do much. On episode 0 of the cart balancing problem, it's probably just hitting random actions for each state and not really going anywhere. But as we learn more and more and more, as we go through the episodes, through this sort of trial and error process of getting rewards back and updating our values and updating our policy, we will eventually be better at the problem, or if the problem has a goal, we will solve that problem. Okay? So that is the overall process of reinforcement learning, what it means to have a reinforcement learning problem. And what remains now is whenever you want to do reinforcement learning, you need two things. You need to take your problem and frame it in the framework of reinforcement learning, in which you have an agent interacting and you get rewards. And the second thing you need is some algorithm or method, or several algorithms usually, that will try and attempt to solve that reinforcement learning problem and actually algorithmically maximize that reward for you. Okay. But first, we're going to need to know exactly how we define a reinforcement learning problem. And in order to define a problem within reinforcement learning, you need to know all the elements of that problem. So, the elements of reinforcement learning problems are as follows. First, you have the agent. The agent is the thing in the environment that's taking actions and making decisions, right? So if you're trying to play chess with reinforcement learning, then you, the player, would be the agent. If you're trying to guide a Roomba around or a robot, the robot would be an agent. You also have an environment, of course, so we know what agents and environments are. We've talked to this to death already. We also have something called a policy. So a policy is going to map states to actions, and I have examples of policies. We're also going to need that reward function. The reward function comes from the environment, and so the environment is sort of the problem statement, and so the problem statement, you are going to define the environment, you're going to define the reward function, and based on that, you're going to update which actions you want to do. We're also going to have a value function, and we have an optional thing, which is the model of the environment. So I'll now describe all of these things. I won't go over agent and environment because we know what those are. But what is a policy? So a policy, in terms of reinforcement learning, is a mapping from states of the environment to actions to be taken at those states, okay? So that map could be a simple lookup table, it could be a dictionary, it could be a hash table, or it could be a complex computation such as a neural network or an arbitrary function. So the policy, all you have to remember about it is that it takes input states and it somehow produces an action from that, okay? So it could be a lookup table, could be a neural net, could be a function with a bunch of if statements. It's just, that's your policy. The policy is really the core of a reinforcement learning agent because the policy defines the behavior. The policy literally says, when you see this state of the environment, you should produce this action. And that's what the policy does. And of course, actions and decisions is what we care about in this course. And the policies may be deterministic or they may be stochastic, okay? And this actually ends up being a really good thing. So for example, your policy will actually be a distribution over actions, usually. So what that means is that instead of having a policy which says, when you're in this state, do this action, right? It'll say, when you're in this state, with this probability, do this action. With this probability, do this action. With this probability, do this action. So it could say, move left 50% of the time, move up 50% of the time. It could say in poker, you want to go all in 30% of the time, you want to fold 50% of the time, and you want to stick 20% of the time, right? So your policy is a mapping from states of the environment to probability distributions over your actions. Okay, so the actual syntax of a policy that we're going to be using. So the policy is going to be represented by pi, so pi for the policy. And the policy at any time step t is going to be represented by pi sub t, okay? The policy maps from states of the environment to the probability of taking an action at that state. So how will we reference that? So if we have our policy pi, and we want to know the probability at time step t of taking action A at state S, that's how we represent this, okay? So pi sub t of S comma A is the probability that the agent takes action A sub t equal to A when S sub t is equal to S. So let me represent, or I'll say that once more. We want to know the probability that we take this action at this state, at this time step, and that is pi sub t of S comma A. Reinforcement learning methods the algorithms that we're going to use are the things which are going to specify how an agent is going to change its policy over time as it learns. Okay? And the agent's goal is to form a policy that gets as much reward as it can over time. Okay? So, let's have an example look at a couple of policies. Here's a sample policy that you're actually going to be seeing on assignment 5. So here we have a pathfinding example. And you know what? Let me actually bring up assignment 5. I think it'll be fun to actually have a look at that. So give me 1 second. Okay, so here is assignment 5. And let me make this a bit smaller. I'll bring this up here for now. Okay, so in this environment, what we have is a pathfinding problem. And I'm not going to explain the whole assignment because what I really want to show you here is what the policy is. So here we have a red dot, and that red dot is the player, okay? And so, or it's the agent in the environment. The player can, or the agent can traverse around the map, and it cannot walk through these walls, but it can walk on the white squares. And its goal is to get to the green squares as quickly as possible, because these are the goals, right? So if we click single iteration here, it's going to start down here in the bottom right. And what these lines here represent is that it's the probability that it should move in a given direction. So at the start, we know nothing about this. We haven't done any learning so far. And so what this is representing is that the agent is going to move with equal probability in any of the 4 directions. So right here, for example, it's going to choose randomly whether or not it should go up, down, left, or right. So here it chose to go up, okay? And then it keeps making decisions based on these probabilities. And what happens if I turn on this for a few thousand iterations is over time, it will learn in what direction it should go in order to most quickly get to a goal. So this is assignment 5, is you're going to implement the algorithm to do this. And what it has learned after a few seconds is the following. So now you see at any of these areas, the policy is represented by these lines. So if you see a full line to the edge, then that means you should with 100% probability go in that direction. And it makes sense, right? Because if our goal is to get from one of these states to a green goal location, then here we would want to go to the left. Here, for example, you can say go up or left with equal probability. Because if you go left, you'll be 1 close to the goal or 1 away from the goal. If you go up, you'll also be 1 away from the goal. If you look here, for example, there's 3 lines. And this says, well, if you go left, down, or right, you'll be 3 away from the goal. So it doesn't matter whether you go either of these directions, so go in either of those directions with equal probability. Okay? So reinforcement learning is cool because as you learn over time, you can dynamically adapt to the environment. So over here, for example, I could insert a wall right here, and until I start learning again, my agent still thinks that I should go to the left. But of course, we know as humans that this isn't true. This is all bad now. But as the agent continues to move around the environment, the values are going to update so that it does point toward the goal locations. So this is what happens. The agent is going to move around the environment. It's going to get a reward signal, and then it's going to produce a policy. So we're lucky in this case that we can actually visualize the policy because it's such an intuitive case of pathfinding. And so that is one example of a policy. So I just wanted to show that. Now let's go back to the PowerPoint. So that is the policy that we'll be using for assignment 5. Here's another example of a policy from Blackjack. So in Blackjack, the state of the game can be represented by the cards in your hand and the dealer's first card. Okay? So for example, up here on the top, you can see the dealer card. So for example, the dealer is showing a 2, 3, 4, 5, 6. And you can see what the cards in your hand are. So you either have between like 3 or 5 and 18 or more. You can have soft 20. I'm not going to go into all that stuff. But essentially, this represents the state of the game, and the policy is what you should do at that state of the game. So for example, if you have 14 in your hand and the dealer is showing a 6, you should stand. That's what this policy represents. So it's just one other way of representing a policy. So as the game, or as the reinforcement learning episodes are going on and on, as you saw with the assignment example, your policy is continuously being updated to be better and to hopefully increase your expected reward over time. Okay, so now let's talk about the reward function. The reward function defines the goal in a reinforcement learning problem, right? So whatever the goal of your problem is, has to somehow be encapsulated within the reward function. The reward function maps each perceived state or state action pair in some algorithms to a single number or a reward. And what that means is that if the environment will have a function or a lookup table or whatever in it, the reward function, and it'll say if the user or if the agent does this action at this state at this time step, this is the reward that that agent should get. So the reward is sort of the desirability of a state, okay? So, or it's actually the desirability of an action at a state. The reward comes from the environment, not the agent. So the agent is not producing its own rewards. If it did, then it could just magically produce rewards out of nowhere. It comes out of the environment. So an important thing is that the agent has no control over what reward it gets. It just, like for example, in real life, you could maybe, if you touched a hot stove, right, you could maybe build up a pain tolerance or say, oh, I really don't care about being burned, but that's not how reinforcement learning works. You can't control the reward signal, okay? The reward signal is coming from the environment and you just have to deal with it. So this reward function, over time, as we go through time steps, we're going to get more and more different rewards. If we sum the rewards over time, what we get is the return. So the return is the sum of agent rewards over time. And the reinforcement learning agent's goal is to maximize returns, okay? Because returns are, it's the sum of the reward over the entire sort of reinforcement learning process. You're not necessarily trying to maximize the next time steps reward. You might have 100 time steps to go. So what you're trying to do is maximize the expected value of the return over time. And in biology, what this sort of relates to in biology is a pleasure or pain model, right? So you're trying to maximize your pleasure over time, not necessarily your pleasure right now. So if someone, you've seen people who like, they don't want to invest any money because, hey, I could go buy a pizza right now, right? And pizza's great, but maybe you're not looking at the maximum reward over time if all you ever do is with your money is buy pizza, right? But pizza's pretty great. Bad example. Okay. So here's some reward function examples. We talked about pathfinding a little bit already. So let's say that in pathfinding, our goal is to get to a terminal state or the goal state as fast as possible, right? So that would mean that at non-goal states, our actions are going to give us a -1 reward. So what that does is that by getting to the goal the fastest, we are maximizing our reward because our rewards are negative, okay? In Blackjack, for example, if we wanted to apply reinforcement learning to Blackjack, if we're at a winning state, we could give a positive reward, maybe +1. If we're at a losing state, we could give a negative reward of -1, or we could give a reward that's proportional to the amount of money won or lost, etc. Okay? So what we do is, if we want to be good at blackjack, if that's what we want our reinforcement learning algorithm to do, we have to shape our rewards to define what is success or what is failure within that environment of blackjack. And those are just two examples, but you can think of a bunch of different examples. Now we'll talk about returns. So the agent gets a reward at each time step. So a reward at time t, t+1, t+2, all the way up. Which of these values do we actually want to maximize? So I accidentally spoiled this whole slide already, but it's not any individual reward that we want to maximize. We want to maximize something called the expected return. And so here we have the return, which is defined as big G of t. So G of t is RT plus RT plus 1 all the way up to R capital T, where capital T is the final time step at the terminal state. So what do we mean by expected return? Okay, so expectation, if you've talked about expected values in statistics, hopefully you have by now, if you've done any statistics course, the problems that reinforcement learning can solve could have randomness in them. Okay, so for example, in blackjack, let's say I have 16 and the dealer is showing a 6, right? I'm obviously going to stick at that state. But if the dealer gets lucky and gets a 4, that doesn't mean that I want to bet the next time I get a 16. Because over time, as you train more and more and more and more, what you're trying to do is maximize the return on average over time. Okay, so expected value essentially means the average value if we could go to infinite time steps. So if the problem contains any randomness, or even if it doesn't, what we're trying to do is maximize the expected return. So that's big E of G of t, because G of t is the return. And if we were able to find an optimal policy, so pi star, remember when we had an optimal heuristic H star and an optimal cost C star? So similarly, we have an optimal policy P pi, or pi star. An optimal policy, if we could find one, maximizes expected return by definition. Okay. Next, we have something called the value function. So rewards are what is immediately good, right? So the reward for taking an action at a given state is what is immediately good or immediately bad. A value function is applied to a state or a state action pair. And value functions indicate what may eventually be good or bad on expectation. Okay? So the value of a state or a state action pair, so whenever I say SA, that's you can consider that doing an action at a given state. So the value of a state or a state action pair is the total amount of reward an agent can expect to accumulate in the future, given that it is currently at this state. And that represents the long-term desirability of a state or a state action pair. So what do I mean by can expect to accumulate? So for example, let's say I'm at a particular state of the environment. And if I choose to go right, then I will always get, let's say, 10 reward. If I choose to go left, 50% of the time, I will get negative 100 reward. And 50% of the time, I will get 0 reward. Okay? So what is the expected value of going left from this state? If 50% of the time I get negative 100, 50% of the time I get 0, expected value is basically reward, or basically the average. So the expected value of here would be negative 50. Okay? So, if I'm here, the expected value of going left is negative 50. So should I go left or should I go right? I should probably go right, because over here, or maybe let's do a little bit of a better example of 100 or negative 100. So if I have 50% probability of getting negative 100, 50% probability of getting 100, my expected value over time, if I can choose left 1,000,000 times, is 0, right? Versus if I chose right 1,000,000 times, I would have 1,000,000 reward, or 10 million reward even. So the value is an indicator of the amount of reward, or the return, right? The sum of future returns that you can expect to accumulate from a given state or a given state action pair. So that's what that is. So for here, for example, the value here, given that we chose a value at random, well, if we chose left with 50% probability and we have a value of 0, and we chose right with 50% probability and we have a value of 10, then the value of this state, given that we chose an action at random, would be 5. Okay, so that's how that works. Okay. Now, in actuality, this value will represent the sum of future rewards, but I just want to show this as a quick example. But we'll get into values in great detail in a future lecture. So, the value function. So, reward is pleasure or pain, right? So, reward, immediately, it's hot or it's not hot. Value, then, is how pleased or displeased we are to be here. So, for example, the value function of standing right next to a really hot stove, you know, you're not super hyped to be there, right? You're not immediately getting that pleasure or pain, but the value, you know, something bad might happen if you're standing right next to the really hot stove, okay? So that's what the value is. So we seek actions that have the highest value. Those will bring us the highest eventual return. Value is a lot harder to determine than reward because we have to calculate it over time, right? We have to do a bunch of trials, we have to get a bunch of rewards, and then we sort of have to average those out. And so we have to calculate those and estimate them. Values we can never know for sure, but rewards we can. So ideally, our policy should have us taking high-valued actions for each possible state. So if we can somehow compute the values of actions at states, then what we're going to do is our algorithm is going to say, pick the action which has the highest value, because that action will maximize the expected return at that state. So here's some value function examples. So let's say we're doing pathfinding again. So a non-goal state on the best path to the goal would have a high desirability and a high value, okay? And that's because actions taking us along that path have a higher value, okay? In Blackjack, if I have 20 and the dealer is showing a 6, that's a very high probability of me winning. And so that state is going to have a very high value because I'm just going to stick, and I'm probably going to win 80 to 90% of those hands when I have 20 and the dealer has a 6, okay? Okay, so those are just some examples of values at the state. Now, here, for example, even though this state has a really high value, I could still get unlucky, right? The dealer could flip over a 10, and now he has 16, and then get a 5 and beat me. But on average, the expected value of this state is high, and so it would have a high value over time. And the last thing we talked about was a model of the environment. And again, this is optional for reinforcement learning. So a model of an environment is going to be it's going to mimic or simulate the behavior of an environment. So, for example, given a state and an action, the model might attempt to predict the next state of the environment. So models are used for planning problems. So we looked at this already. In order to do algorithms like A-star search or alpha-beta search, we actually have to have a model of the environment. We have to have the game of Connect 4 programmed in order to do this tree search, right? Because we have to have the ability to save states, to unroll recursion, to go to the next state, to evaluate states. And so the one problem, well, not the one problem, but one of the major drawbacks of algorithms in heuristic search, like A star and alpha beta, is that you require a complete model of your environment. And so it's very hard to apply A star algorithm or minimax algorithms to real life problems where you have to deal with, for example, real life physics, etc. However, in general, you do not need a model of your environment in reinforcement learning. All you need is the ability to say, okay, at this state, I got this reward, and therefore maybe I should or shouldn't do this action again in the future. But if you do have a model of the environment, it just means that you can, throw that model into a computer and you can simulate it really, really, really fast. Okay. So I'll tease this a little bit now, but this will be almost the entire topic of the next lecture. And this is the topic of exploration versus exploitation. So one of the main challenges in reinforcement learning then is the balance between exploration and exploitation. So what the hell does that mean? So to obtain a lot of reward, agents have to prefer actions that it knows produce good results. So what that means is if I know that this action has a certain value that's higher than the value of another action, then I should probably be taking that action in order to maximize my reward. But the catch-22 is that in order to learn which actions produce good rewards, you have to try them first, right? You can't be sure, like, for example, I'll give an example later, but you can't be sure which action is actually better until you've tried it a significant amount of times. And so the agent must exploit knowledge that it currently has, but also explore other actions in order to gain more knowledge. And this is actually one of the main challenges in real life as well, not just in reinforcement learning. You can almost look at life as a reinforcement learning problem. So who can give me an example, a real life example of exploration versus exploitation in the chat? Can anyone come up with an example of that? I bet you that you're going to say one of the two things that I have on this slide. Every other year that's been the case. So an example where ideally you want to choose, we can go back a slide. So ideally you want to take actions that you know will produce good results, but you also need to explore, okay, in order to find new actions which may have better results than what you're used to. Okay, so I got the answer that I was looking for. So thank you for that. Choosing a restaurant. Okay? So all the other answers are good as well, but this is sort of the canonical example. So you have not visited every restaurant in the world. Probably. Okay? Or even all the restaurants in St. John's. And so let's say you want to go out for dinner. What are you going to do? You're going to have to make the decision. Do you go to the place that you know is okay? Or do you go to your favorite restaurant? Or do you go to a new place in hopes of maybe finding a new favorite restaurant, right? Because if you think about it, yes, you have your favorite restaurant that you've eaten at a million times, but that wasn't your favorite restaurant until you went there. So saying that it's always going to be your favorite restaurant forever is kind of foolish, right? So this is exploitation. So exploiting would be choosing your current favorite restaurant. You know it'll be decent, so you're going to go there. Exploring would be choosing a new restaurant or a restaurant that maybe you went there before and it wasn't so great, but you'll give it another try. Okay? And some people also had some game-related examples in the chat, and those were good. So, for example, playing games. So last time I chose door number 3, and it had 10 gold pieces. So do I choose that the next time, or do I choose a different door in order to see if I contain more, right? So exploration versus exploitation is a really important problem. And what we're going to do in the next lecture is we'll talk about, I think it's the next lecture, is we'll talk about something called Bandit algorithms. And Bandit algorithms are a set of algorithms that will allow us to solve, not necessarily solve, but at least help us with the problem of exploration versus exploitation. Okay? So that's where I'm going to leave off right now. And if I go back to the course, so yes. So that was sort of the introduction to reinforcement learning and what it is. In the next class, we're going to be talking about reinforcement learning and Bandit algorithms. And then we will go into different algorithms that'll allow us to work on assignment 5. Okay? So after that, we'll talk about neural networks and deep neural networks, and we're actually going to do something really cool where we tie reinforcement learning and neural networks back together, and we're going to talk about something called deep reinforcement learning. But we won't get too deep into that. So someone said, so high reward means high probability of achieving the goal in the shortest amount of time. That would be a high return. Okay, that's a high expected return. Reward is what you get immediately at the next action. Expected return is what you expect to achieve over the life cycle of this experiment. Okay, so yeah, so you can just type !playlist if you want to see the lectures again. And I'll be posting this lecture on YouTube, and you can see all the lectures there. So that's it for this lecture. Thanks for tuning in, and it will be at the next lecture will be at the same time on Tuesday evening.